calculation 两做法，那点帮你治疗的，就是不是很多的 theorem，
嗯
可是 x 可以在上面有这个 t 就可以，这个 x 可以挡住。
嗯，那样这是突然，对不对？这是突然搬到这个 x 的东西了。可以，
对对 t 做
嗯
integrate，
嗯，然后你再and then 你才 differentiate，
x 可以给它搬，这样子搬出来可以了，
因为它是 scalar 嘛，它是，
变这样子啊，
嗯嗯
这边是跟零，
嗯哼嗯哼嗯，这水了，
那个 mathematical analysis，
还在做这种题目
没，还有很多 proof 前面你看，
啊，
这个是有难要有一点简单的嘛，
嗯，
不然我分数就很低了，人家
了解，
是挂胡啊，
嗯哼
难。三可以搬出来，
嗯
然后这边定出这个
嗯，
这个卡，
很难，differentiate 是成，
对哦，做是
对对对
integration 机，
对，其中一个可以看到的东西是那个三的出现。
对，
哦，OK 了，暂且不挑，还有其他挑。嗯
这有两个 variable，这个看作 skill 的在哪？
嗯嗯哼，
这只有一个嘛，
没事，
你只有一个题嘛，就
这个是
这个先
龙体，
放进去嘛，
没有这个龙体，integrate 龙体，
先 integrate 问题先，
对啊，
这边放个 e，它
嗯，
之前有一个东西，
就这样哦，
之前学一个 theorem 是什么？
嗯
我有点忘记了写啊，
嗯哼
还是这边写 a，然后
嗯哼
这边是
嗯
x 的
哼
东西，然后这边 f e
嗯哼
e
嗯哼嗯
这样子，有一个公式，
哦呀，对对对，这
这个有
个应该没有这个东西，这个剪掉这个，这样子，哎，就这个东西来的，这个不是 F 啦，其实这个要一个大 F，所以意思是说这个小 f 是这个大 F 的 derivative，就是你在做的东西。
嗯
因为你看你 differentiate growth 是这个二题嘛，
这个就
and then fundamental theorem
second
calculus，
fundamental 有人讲
没有 second 它就叫 fundamental theorem of calculus，
跟第二
好像有，但是
second，
我忘记了。
对，还有第二个，这个就用第一个就可以解了，
可以，
我用第一个解，第一个解，
嗯
啥对？边这个嗯，
嗯，一个题耶，
有
嗯嗯，
有
三个 v 嗯
有
嗯哼嗯嗯嗯嗯哼
我这个
嗯哼
这边零，
嗯哼
对，它这个
嗯，
这个
就这样，
很简单好了，
嗯
我给这个。
嗯。 thing. So I put out the lecture notes for last lecture. Please have a read. Okay. Question on group action stuff. Any part you don't understand before the rest come, we can discuss, or assignment stuff you want to discuss. Anything you want to discuss? Or any other idea that you thought that you want to clarify? Is the assignment going okay or not? Still have 2 office hours, you can come and see me immediately. Okay. Yeah. You have problem, just come to my office hour. Yeah. We can solve it there. Mm-hmm. Action same as law of composition. Okay. So what's the difference between group action and law of composition? Okay, so you have 2 things, right? Okay, so what are these 2 things? Okay, so both of these are also are map, right? So these 2 are map. And define of groups. Okay, what is the map here? So this map on law of composition is G cross G to G. Okay, where G a group. For group action, what do you have? We have G cross S to S. Okay, so what is S? What is G? So G is still a group, but S is just a set. Okay, we don't know whether the set can compose or not. S is a set. And then what does law of composition have to satisfy? Pretty much nothing. Nothing. Just a map. Nothing. Just a map. So G1, G2, I just compose them together. Okay, so that they are in the right space. Okay. And then how about group action? Okay. Group action, you took something in G, okay, something in X, and then you compose together. This thing is in S or in G. This is the thing in S. Okay. It becomes something else in S prime. Okay, it becomes something else in S. Okay, so meaning we are like playing around with some set using group. So you can see that G is also a set. So it is possible to take you could take you could take G equals to S, okay? But sorry, take S equals to G. Okay? What's the group action you need to satisfy? Group action axiom. There are two axioms you need to satisfy. Right? So the first axiom is the identity in the group should fix all my elements. Okay, should fix all my elements. Okay, axiom 1. How about axiom 2? Axiom 2 is associativity. So meaning if I take a product of elements in my group, okay, how this thing gonna add on my set? Okay, how this thing gonna add on my set? I add them one by one. Yeah, add them one by one. And this, okay, for all things. Okay, so if let's say if I take my set as G, okay, my set as G. So here become G, 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 G. So what are these? If I make the first axiom an element G here, identity type G equals to G. This is just the normal law of composition in my group, okay, which is the identity element. And then this one, if I make S a G, this is what? This is associativity in the group. Okay, but if when it is a group, this law of composition has to be associative. Okay. Yeah, so actually this G here might not be a set also. Okay. Generally not group. Okay. Generally it's not group also. Okay, law of composition. If it is a group, if G is a group, then the LOC is associative. The LOC is associative and satisfy. Okay. So I mean, so law of composition here just tell you how to combine two things without any restriction, no restriction. Okay, but group action here, because you see the name here, group action. So you need to start with a group. Okay, add on some set. Okay, and then what's the thing? What's the new thing you get? Set. So how you should imagine this? It is like it is like you have something like, let me see. So for example, this okay, this rubber, what's it called? What's this called? Yeah, duster. Okay. So let's call this duster, right? Okay. So how you move this duster around, you still get this duster. Okay. You can rotate it. You can translate it in this vector space, or you can bend it. Okay, you still get better same duster. Okay. So the action is like a group. Okay, action is like a group. And then set is some element. Okay. Okay. So you should think of this group action really an action. You are doing some action on some object. Okay, but you preserve that object. You don't deform that object. or destroy the object. Okay. Alright. Okay. Yeah, so this is the idea between these two. Alright, so let's continue. By the way, some of you say sometimes too colorful, right? Why I make this thing so colorful? Because I really want you to think differently. When you see examples, when you see theorem, when you see definition, when you see remark, you should really think differently, you know. You cannot just read it plainly like that. I want you to think differently in your mind. Definition is something must be true. Okay, cannot change. But theorem is something need to be proven so that we can use it. Okay, and then what's the proof of it? Okay, proof might not, proof is as important as theorem, but you need to understand the theorem first before you can prove it. Okay, so theorem is where the most important, and then proof is the thing that help you to understand the theorem. Okay, and then example, how about example? Example help you to understand the definition better. Okay, so you need to split these things out. Okay, so that you have a right idea what's going on. Otherwise, you just read plainly, then you mess up all of these things together. And you can get confused easily. Okay, Anna? Hi, where are you from?
As of now, go find my sergeant from
So you found it eventually.
found it.
Okay, good.
You're so handsome today.
Thank you. Okay. Yeah. Okay, Anna. Okay, so when you see this statement, right, please split them out. Don't confuse yourself. Don't mess them up together. Okay? I really want you to think differently when you see those statements. Okay. So just now we talk about group action on X. We can talk about a specific S. Okay. So what kind of set we have just studied? The set of coset. Okay, we can study the set of coset. So let's take this S to be the set of coset. Here we have this action here. So how should I define this action? How should I define this action here? How should we define this action? How should we define this action here? Hmm? How should we define this action here? Hmm? So you have an element in G, you have a coset. So what can you do? What can you do? I'm easier. Multiply them. Okay. But this is a set, right? So how do you multiply them? Hash is a set. A hash is a set. So how do you multiply them? You just multiply G with A. You multiply with the representative. Okay, and then show that this is actually well defined. Okay, you don't send to a different number. So you send to GAH. Okay. So in your mind, you should have one example at least in your mind. Okay. So the easiest example is Z times Z mod, for example, and 3Z, for example. Okay. So what is Z mod 3Z again? So these are the set of coset, which is like 0 bar, 1 bar, and 2 bar. Right now. Okay. So how do I add, for example, 3 on 3 on, okay, let's not add 3, let's add 2. 2 on 1 bar. What happened? What happened to this? So you pick the representative from 1 bar. So what's the representative from 1 bar? What's the representative from 1 bar? What's in 1 bar? 1, right? Okay, so you can take 2 plus 1 bar, which is 3 bar, which is 0 bar. So meaning 2 add on 1 bar get you to 0 bar. Yeah. Okay, so you can take all the element in Z, okay, and then add it on the coset of Z mod and 3Z. So are you confused why this notation seems a bit different here? I put bar, but the top I got H. Anyone confused with this? Confused, Michelle? Michelle, did you not done? Yeah. No, confused, you just say confused, it's okay. Never mind, nothing wrong one. Okay, I won't condemn you. Okay, I won't condemn you. Just say okay. So that other also feel the same. Okay. So actually I can also write in this form, H form. So how do I write in the H form? What's the subgroup that I mod up in this case? Z mod. What's the subgroup? The normal subgroup that I take to quotient. Z mod 3Z. 3Z is a subgroup, right? Because if you add 3, 6, 9 together, they all are multiple of 3 again. So 3Z is a subgroup. Okay. And then 3Z is normal. Why 3Z is normal? Normal means what? The conjugation of every element live in the same subgroup. Okay. So for example, 3 conjugate by 2 is what? 2 plus 3 minus 2, which is 3 again. Why is this always true? Because Z is abelian. Okay, so you can straight away cancel the G and G first. Okay, so you're left with 3. So in abelian group, all the subgroups are abelian. In particular, 3Z is normal. Okay, sorry. All the subgroup of the abelian group is normal. Okay. So I can write like this: 3Z, 1 plus 3Z, and 2 plus 3Z. Okay, I also can write in this form here. Yeah. Okay. Is everyone okay with these equivalence classes? Okay. How about the rest? So okay with the equivalent classes here? Yes. Okay. 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 And then we can try more. Okay, let's try more. Let's try more. So we somehow send 1 bar to 0 bar. Right. Okay, so this means what? This means what? 0 bar is in the orbit of 1 bar. Because I can reach 0 bar. Okay? I can reach 0 bar using 1 bar. So meaning the orbit of 1 include 0 bar. Okay? And then what else I can try? And I can try. How about 1? How does 1 add on 1 bar? Okay, let me try test 学妹. Yeah, how does 1 add on 1 bar? How? Look at what I do here. How to add on 1 bar? One plus one, and then I took the bar. Okay. So 1 plus 1 bar is what? 2 bar. Okay. So I get from 1 bar to 0 bar. I get from 1 bar to 2 bar. So this means that the 2 bar and 0 bar is in the orbit of 1 bar. Okay. I can reach from 1 bar to 0 bar to 2 bar. Okay. But also, of course, 1 bar is always in the orbit of 1 bar itself. Okay. So 0 plus 1. So, okay. So this means what? The orbit of 1 bar. Okay, let me write the name first. The orbit of 1 bar is 0 bar, 1 bar, and 2 bar, which is what? Which is the entire set of cosine. Okay, so there's only one orbit. Okay, for this group action. This means that this group action is transitive. Okay, this group is transitive. Okay, this group action is transitive. Okay. So since there's only one orbit or 1 bar equals to z mod 3z, this group action is transitive. Okay or not? Okay. So remember how you think about orbit. You think of how the Earth orbit around the sun. Okay. So you think of the path that it orbits in. So where can this Earth move to along the path? Okay. So orbit of 1 meaning where can 1 move? And then coming back to 1 again. Okay, so think about this number here. So if you add 0 to 1, okay, you stay at 1. But if you add 1 to 1 bar, you go to 2 bar. If you add 2 to 1 bar, you go to 0 bar. And then you can add 3, 4, 5, 6, 7, and keep adding. But you still orbit around this set, the element here. You're orbiting around here. You get it? If you don't believe, you can try more number in Z. For example, you want to try -3, right? So -3 add on 1 bar is what? -2 bar. So what is -2 bar here? -2 bar is the same as what? -2 bar is the same as 1 bar. Okay, so it's there at 1 bar. And then you can keep doing. Try all the Z here. These are the only places you can go. Yeah. Okay. So this is why it calls an orbit. Because you're orbiting around this element. Yeah. Yeah, you can work it out. You can try and work it out. So maybe we just try one more. Okay, let's try 2 bar. Okay, let's try 2 bar. Where's so try and find the orbit of 2 bar. Okay, so let's find the orbit of 2 bar. So we have Z cross Z mod 3Z to Z mod 3Z. Okay, how about 2 bar, right? Okay. So you can try a few numbers, right? Okay, let's try 0. Let's try 1. Let's try 2. Okay. You know why I don't try 3 and so on? Because if I do 3 plus this 2 bar here is the same as 0 plus 2 bar. Okay. Because on the set, 3 is equal to 0. Okay. So these are the 3 main things we should try. Okay. Different things. So what is 0 plus 2 bar? What is 1 plus 2 bar? What is 2 plus 2 bar? Okay. What is 0 plus 2 bar? It's just 2 bar. 2 plus 1 bar? 3 bar, which is 0 bar. 4 plus 4 bar? 1 bar, because 4 bar equals to 1 bar. So orbit of 2 bar is also the whole set. It's also the whole set. Okay. Yeah. There's only really one orbit for each coset. Okay. You know why is this true? Huh? Yeah. Follow-up question. Yeah, you want to ask this? Same. So what happens if you put 4? 4 plus 2 bar is what? 6 bar, which is 0 bar. You know why these two are the same number? Sure, remove the 3, but you should note that 1 and 4 are the same in mod 3. Okay, no? Yeah, these two numbers are the same mod 3. Because 4 equals to 1 mod 3. Now, every number in 3z form is equal to 0 bar. 3z plus 1 is equal to 1 bar. Yeah, sure. 3z plus 1 plus 2 bar is 0 bar. Yes. Correct. Yes, you're right. Yeah. But the other argument is you already reached everything. You cannot do much already. You already reached everything already. This is the whole set already. You cannot try more and then think that can I go outside? Cannot, because these are the only thing you can go to the set, right? You already reached everything in your set. Your set only has cardinality 3. You understand? Yeah. You already have where to reach all of them. You don't think that I haven't tried all of them and Z is infinite or how? Right? Because you already reached all of them. That's all. You cannot do more already. You get what I mean? So this is by the cardinality argument. This is finite. 3 of them only. Okay. So why is this true? So we pull back again. Why is this transitive? Is this always transitive for every set of coset? Is it transitive? What does set of coset do? Do you remember? What does coset do? Partition the group. Partition the group means what? Every element in the group. Please remember about the cutting cake procedure here. So you cut your group using H. Right? So you go H, AH, BH, CH for example. So meaning what? Every element in G live in some of this one and only one, not just some, one and only one partition. Okay? But now what do? You take your element in G, go and add on this coset here. Okay. Yeah. So it will permute the coset. Okay, it will permute the coset. Permute the coset. Why is it permute? Permute means bijection. So meaning G multiplication by G is a bijection. Why multiplication by G is a bijection? Because G is invertible. Okay, inverse axis for the multiplication. Okay, so it permute the coset. Okay, no? Okay, so we just take one proposition and then we won't prove it. I think I will provide in the lecture notes. So if you have a subgroup, okay, you consider the coset group action, okay, coset group action. then this section is definitely transitive. Okay, it's definitely transitive. And then, what's the thing that fixes H? What's the stabilizer of H? Now, what's the stabilizer of H? What's the elements that multiply to the, when you add on the subgroup H, okay, you get H. Just H, okay? So everything in H, so this means that everything in H, and then H add on the coset AH, okay, sorry, the coset H is equals to H, which is just H. Okay. And so this is the one sentence. This is for the direction GH is in H. GH contain H. How about GH in H? Okay. So you need to show that for all X in H, such that X on H that maps to SH when SH equals to H implies that so X is in GH implies that X is in H. Okay. So this is the two things you need to prove. Get to prove B. Okay. Yeah. Okay. No. Any question about these two statements or the proof? Okay. Yeah. Okay. Okay. Let's go to the next bigger theorem here. So let's do this orbit stabilizer theorem. Yes, let's do this stabilizer theorem. Stabilizer. Okay. So let's consider a group G. Okay, acting on a set. Okay, so S is a G set. There's a group action. And let's take one element from your set. Okay. Then the statement is there exists a bijective map. There's a bijective map. Okay, let's call it an epsilon. Okay, epsilon from G cross GX to OX. So what is GS? GS is the stabilizer. Okay, stabilizer of X. So meaning all the group element that fixes S. Okay, and then we prove that stabilizer forms a subgroup. Okay, since it's formed a subgroup, right? We can use subgroup to partition, right? G, or this subgroup form a coset. Okay, so we consider set of coset here. The result is this set of coset here is bijective with the orbit of S. Okay, so you should think about it. Here, these elements, this coset is something represented by the group element. But OS here is what? OS here is a subset of the S. So somehow you study the group element using the set. Okay. So let me draw some in here. So so here OS here is a subset of S. Okay, and then G cross GX here is, okay, let me use different color then. So this is subset of S. This is represented by group element. Okay, so on the left hand side here, something in the group. On the right hand side here, something in the set. We try to build bijection between these two. Okay, this is quite astonishing, you know, because we are trying to relate two different structures together. Okay, yeah, and so we have more than that. Okay, we have more than that. This bijective map is special. Okay, this bijective map mute, okay, with the action of G. Okay, what do I mean by commute? Commute means AB equals to BA, right? Okay, so what's the thing that commute here? Okay, so let's say we take two elements from G. Okay, so epsilon on G acting on AGX, okay, is the same as you go and do epsilon on AGS first, and then you add on G. Okay, and actually I haven't told you what this bijective map is. What is this bijective map? This bijective map here is sending a coset. So here is a coset. Okay, on the left hand side is a coset. On the right hand side is a set. Right. So if I have a coset here, what do you think the thing in the set you should send to? What's the element here you need to send to? If I have AGS here, for example. Because this is obvious, so what's the thing you can add on S? You could just consider A S. You just consider X. Okay. Just take the group element A and then add on an X. Okay. It is something in all S, right? Because all S is somewhere that S can go. Okay. Makes sense. Any question about this statement here? Maybe meditate a bit and see, do you understand the statement? Any word you don't understand and any part you don't understand about this statement here? Yeah. What's the meaning of this, right? What's the meaning of this? Normally we can slash by what? H. So what's H? H is a subgroup of G. Okay. So normally we slash by H. H is a subgroup of G. But GX, what is GX? Is GX a subgroup of G or not? To ask this question, you need to understand what is GS. GS is what? GS is the stabilizer of G. What's the stabilizer of G means? All the elements in G such that it fixes G. So it means G little s. Okay, G of S element equals to the element itself. Okay, G little s equal to little s. So that thing form a subgroup. Last time we had seen. Okay. The stabilizer of each element form a subgroup. So if it's a subgroup, then you can consider the quotient group. The set of coset. Okay or not? Okay. So you need to make sure the thing that you slash out is a subgroup. And then we can consider the set of coset. So this is a set of coset. So here the element here is coset AH. So H here is GS. Okay. Okay. All right. Okay. So actually we have a more compact way to say this thing. Okay. So what is this? You see, remember last time we see something like this. We make it into a like there's an order of doing this epsilon, right? Okay, we can similarly write this as a commutative diagram. Okay, remember last time when we do the homomorphism, we multiply first and then do homomorphism, or we do homomorphism first and then we apply. So there are like two ways to reach the same thing, and we can turn this into a commutative diagram. Okay, let's turn this into a commutative diagram, and then you can understand this equation better. Okay. All right. So let's see how we turn this into a commutative diagram. So let's draw the square first. Okay. So first, what do I have? Okay. So let's read this. Perhaps read this first line, the left-hand side first. So we start with AGX. Okay, AGX. So AGX live in the set of coset here. Okay, AGX live in here. Okay. So what can I do? I apply G. Okay, let's apply G. Apply G on AGX. So if I apply G on AGX, what happened? Just now we discussed already. You are commuting the coset. So you still live in the world of coset. Okay, so you are living in the world of coset. G and GS. Okay, so in other words, this is a multiplication map. So if I go down, I use multiplication map. Okay, and then apply this epsilon here. Okay, what does epsilon do? Epsilon send AGX to AS. Okay, so meaning I go to somewhere in OS. Yeah, I go to somewhere in OS. So let's apply epsilon to it. And let's apply epsilon to it. I get epsilon on G on H. Okay, so this is the first path I have. How about the second path? What do I do to AGS first? I use epsilon. Okay, what does epsilon do? Epsilon send the coset to something in the orbit. Okay, so I send AGX across to epsilon of AGS. Okay, so meaning when I go horizontally, I apply. So what's the next thing I do to epsilon AGX? I multiply by G. So I multiply by G. So I multiply by G, G dot epsilon of AGX. So when I'm going down, I use multiplication by G. Okay, so when I go down this diagram, I use multiplication of G. When I go horizontally, I apply epsilon. Okay, and then when we say the group action commute with the map commute with the epsilon, that means these two things are equal. These two things equal. Okay, so when you're going two paths and then they are equaling, this means that this diagram commute. Okay, so this is a commuting diagram. Okay. Okay. Yeah. So when the final product here is equal, this means this diagram commute. Okay. Okay. Any question about this commuting diagram? with this equation here. Okay, so this is a convenient way to talk about this equation here. Talk about this equation here. So actually, you see from this picture, right? See from this picture here. Does G mod GS has the action of G? Can you add G on G mod GS? That's right, because we said that G can add on the set of coset. Is there an action on all S? G? Yes, right. Because G add on S. Okay, so it add on the orbit of X. Okay. So there are action. Okay, so there are action on set here. Okay. Yeah. So this is the big picture what is going on. Okay, with this map. Okay, so this is the big picture what is going on. Okay, so there are some terminology I want to introduce. So we will say that the map epsilon is compatible with the group action if if it commutes with the action. Okay, if it commutes with the action, we say it is compatible with the group action. Or there's another way of saying it. Okay. Or I will say that the map epsilon is an G equivariant G equivariant. Okay, if you commute with epsilon. Yes. Oh, sure. What does it mean by compatible with group action? Okay, so the thing behind it is the definition when it commute with the action. Okay, so this is how you read it. Compatible with the action, I won't tell you actually. So it is compatible with the action if it commutes with the action. But I already tell you what it means by commute with the action because this is in this statement here. Which commutes with the action? That is this part here. And this means commute with the action. Okay, which is the commutating diagram I draw to you. And we also said that epsilon is compatible with the group action if it commutes. Okay, so there are three terminology to talk about a map commuting with an action. So you can say that epsilon is compatible with the group action. You can say that epsilon is an G equivariant map. Okay, and then epsilon commute with G. These three things is the same thing. But I tell you one of them already, which is G epsilon commute with G action. Does that make sense? Yes, sir. Okay. Good. Okay, yeah. Okay, good. Any other questions? Any question before we prove this? Okay, so let's prove this. So what do we need to show here? So we need to show that there exists a bijective map. Okay, so we need to define this map here and then show that this is bijective and then show that it commutes with the group action. Okay, there are a few things to show here. Okay, no. Okay, so you need to check that this map Okay, it's bijective. It's well defined also because you might start with different representative and then show that it commutes. Okay, so let's come to. So let's rewrite our map first. So define epsilon from G mod Gx to Ox. Okay. So what's this map here? I send the coset A G little s to AS. Okay, so this is my map. So first thing we can show is the easiest thing to see is it commutes with the action of G. Okay, we will show that it commutes with the action of G. So let's bring this equation down. So to show this, what do we need to check? To show this, so we check that G check actually GA on S is equals to G of S. Does everyone see this? To check this equation here is equivalent of checking this. Because this is my map. I send AGX to AS. Okay. So AGX here become also here, okay. Maybe I need to be a bit careful here. So here's G dot A GX. Okay. So I send epsilon of G dot A GX to where? G dot A GX to G dot A times X. Okay. Then here I send AGX to S and then apply G. So the difference between these two is just a axiom of group action. Okay. So this is GA acting on X is equal to A acting on S first and then act by G. This is by the group action axiom. Okay. Chris, are you still on the line? Then, if not, you have to ask. Otherwise, you will lost completely. Please ask. Like Zerxian like that. Okay, just ask. Okay. Yeah, because otherwise, if you don't ask, I cannot help you one. Definitely, I can help you. Okay, if you want to get help, please ask. So, is everyone okay with this? So this is true by axiom of group action. So which is by axiom of group action. Okay. Okay. Why is this easy to show? Because the definition make it easy. Okay. Otherwise, if you try different definition, then you have to check different. Okay. No. Wizard. Okay. So 2. So now we need to check our map whether it is bijective or not. Okay, we need to check whether the map is bijective, whether the map is well defined. Okay, is it well defined or not? Okay, because we can write our coset in different form. Okay, for example, just now Z mod 3Z. 1 bar has different form. I can write 1 bar as 4 bar, and then I can write it as 7 bar. Yeah, correct. 7 bar, 13 bar, all represent 1 bar. Okay. So we need to show that it is well defined. So show that the epsilon map is well defined. Okay, which is AGX to AS. So let's say I have AGSM equal to BGX. Does it imply that AX equals to BS or not? Okay, so suppose I have the same thing in my domain. Okay, I want to show, okay, the thing in the codomain is the same. I have to show this. Does this look familiar or not? Does this look familiar or not? Look familiar or not? Since the two coset is the same, what do I have? I have A minus B is in the stabilizer of X. A, B is in the subgroup H. Right now. Okay. Then what does it mean? If it is in the stabilizer of GS, what does it mean? What does it mean? This means that A inverse B fixes S. Okay, A inverse B fixes S. And this implies that Bx equals to AX. Okay, no? Okay. Is it okay? Okay. It's following, everyone following? Okay. So this is for well-defined. Two things A equals to B implies phi A equals to phi B. Okay. A equals to B implies phi A equals to phi B. So you assume two things are the same in the domain, and then after the map, they are still the same. Okay. How about injective? Injective is the other way around. If I have two same image, they have to come from the same thing. So if phi A equals to phi B implies that A must equals to B. Okay. So you start from AX equal to BX, and then you need to show AGS equal to BGS, okay, for injectivity. But this argument, right, you can go from the bottom all the way up here. Okay, so this argument is here is if and only if. You can go reversible. So that means you can go from BX equals to AS, and then you apply A inverse to both sides, and then you got this. And then you know that A inverse B is in the stabilizer. And then since A inverse B is in the subgroup, meaning what? A GX, B GX is the same coset. Then you can go backward. This is what we proved last time. Okay. Is it okay? Okay, so what do I want to comment here? So B, by reading the above argument backward, and it shows that epsilon is injective. Okay, it's injective. Okay. Okay. How about surjective? How about surjective? Is it surjective or not? So if I give you anything in the orbit, can you find me a coset that map to it? Huh? Can you do that? Can you find such A or not? Can you find such A and then build the coset? Can you do that? So what does it mean by in the orbit of S? It means that there's something that add to S get you the thing inside the orbit. Okay, so let me write down. But for all x prime in OX, okay, it means what? You can reach your x prime by acting on S by an element A in G. Okay. Then you can write every element in terms of some group element times X. Okay, then what's the pre-image? Okay, what's the pre-image? What's the pre-image of AS or S prime? Then epsilon of AGS, okay, is equals to AS, which is S, okay, which means AGS is the pre-image of S prime, again, under the map epsilon. Okay, so it is surjective. Okay, so for every image here, I found something that mapped to the image. Okay, why I can do that? Because of the definition of the orbit of S. Okay, orbit says that I can reach to all the elements just by the action or the multiply by a group. So there's something that I can move this S that reach every element in the orbit. And then this group element A here give you the pre-image. Okay? Any question on this? Any question? No? How about we take a break and then we will look at one example of this theorem. Okay, let's come back at 9:12. In the meantime, maybe I'll take attendance. Venus 乐天伟泽安儿严科is here, here. Not here. Sorry. Raylan will meeting later, right? Okay. 至于 Seng what happened on Monday? Sleep, okay. 顺林 go Thailand, okay. 海人 金波 go Thailand. Wayne Ishan not here. Ingji, yeah. Hey, Ishan, just call your name. 可以 Xian 江业李凯袁家文硕一定玉维呀燕博 yes 陈业 OK 林金 OK 孔杰呀宜州 yes 丁宇呀李晴 yes 曾成 yeah 说宁 OK 武力 OK 武力天德轩明明 Grace 三叶嘉文嘉文明修 Michelle Brian yeah Ellie Jermaine Yeah, Ziyan. Okay. Ziyan, you also not here on Monday. Why? Sick. Okay.
这个考虑，跟之前我们第一门的考虑不一样。
一样啊，它 commute 是 epsilon 跟这个 G 的 action commute。你看，对，你看 epsilon G 先做，再做 epsilon 和先做 epsilon 再做 G 是一样的。
epsilon 不是一个
map，对对对，所以就是有点神奇在这里了，一个是 map，一个是乘法，所以我们重新 define 了，所以什么叫做 commute with the action of G 就是这个东西。
这一个那个
说说看，
因为它是一个是一个那个宝贝
对
然后那个 map 为什么一个
什么一个 map 就是这个 map 吗？因为你要 define 一个 map 嘛，你只要告诉我这里的东西怎么送去这里。OK，这里的东西长怎样？这里的东西都是一个 concept。这些东西长怎样？这里的东西是 element of x。OK，所以我怎么从这里造一个 element of x 给你呢？我就拿我的这个 representative A 乘上这个 s，这个 s 是活在那个 set 里面的东西嘛，所以你拿 group element add 在 element s 上面会做什么 ？group action 会给你一个新的东西在 s 里面。对呀、然后这个东西就是活在这个 orbit 里面咯 orbit 是这个 s 可以去到的地方，所以 as 是活在 orbit 里面咯，所以这个是我造的 map 咯。然后不 trivial 的东西是为什么这个东西是一个 bijective map？
我通过这个
对，
反映所有的一个 map 都是摆下去。
没有，只有 exist 一个吧，exist 就是这一个是一个 bijective，其他没有。exist 罢了。Please take care yourself, because I realize the atmosphere or environment in the school, right? Sometimes will become very down. You know what? It's like how to say I don't know you realize or not. Sometimes when you wake up, you feel very hard to wake up. Actually, this is not just you feeling that. There's quite a lot of them feeling the same. For example, just now I received a message from Eating says that he cannot sleep last night for no reason. So you are the same, right? So you need to be really careful in the school. This environment here is kind of tricky. Not just study is tricky. This environment also tricky. Your neighborhood, private, play games. Do the dirty stuff. Okay. Call the police. Several times. Call the police. Okay. And then, right. So you need to please take care of yourself. Otherwise, you really easily drop into these, how to say, yeah. You will feel very uncomfortable. So please live well with the environment here. Otherwise, you will be easily affected. Affected by the environment here, atmosphere here. Yeah. Did you live inside the school? Yes. Oh, you live inside the school. So I mean, this environment is, I feel, a bit tricky. Why? Because did you feel sometimes when you wake up, it's very hard to wake up? No, man. You are very easy to wake up, then you are good. You are good. You are not in my category. Then you are good. For those who feel very hard to wake up sometimes or what, I mean, this is not just you. It's like how to say, it's like a magnetic field here, you know, the magnetic here, the vibe in the school. Because at this school, it's really wet. It's very wet. House very wet, you know. Everything can grow more, you know. Even my soy sauce also grew more. I never use it, but it grew more. Soy sauce, or you know, grow on the liquid, you know. Really inside the liquid, I can show you the picture. I never use it, but it still grew more, you know. It's crazy, you know. It's crazy. Okay, this here is really wet. Okay, you know, water is a symbolism of life. Okay, so something can affect you a lot. Okay, this water vapor, please take care of yourself. Okay, yeah. Yeah, so if you want to excel, you need to live well with your environment. Your environment is very important. And then your environment will give you intuition. Okay, so please study your environment well. Live well with your environment. Okay, so let's look at one example of this theorem here. Okay, so what does this theorem tell you? There's some bijection. Okay, there's some bijection between the set of cosets and orbit. Okay, let's exhibit this theorem. Okay, let's exhibit this theorem in one example. So we need to pick some G. We need to pick some S. Okay, and then we need to pick some stabilizer. Okay, so let's do it. So let's pick G equals to S3. S3. Yeah, let's pick this set here. So this set here, there are two, at least two presentations I gave you already. Okay, one is the obvious one. Okay, this is the permutation of 3 indexes. The other I give you as a free group with generation. Relations. Okay, free group with relations. Okay. Y equals to 3 because of identity. Okay. So I give you two of this. So this we want to consider one subgroup here, which is the group generated by 1 and Y. So meaning I take the let me see, let me see. What is this? Let me check. Okay, so Y is the thing that gives you the so let me change this then. So let's keep with the same notation we have last time. So we put x squared here, x here. Okay, so pick this cyclic sum. Okay, let's pick this. All right. So what are the left coset here? So you see, try use your knowledge now, please. Okay. So last time we say we need to understand the knowledge, right? We need to put things together now. So we have subgroup H. Okay, subgroup H partition G. Okay. So there are how many number of left sub coset now? What's the counting formula you have? Number of left coset times the cardinality of the subgroup
equals to the cardinality of the group. Okay, so the cardinality of H is 2. The cardinality of your group is 6. So how many left subgroup you have? 3. Okay, so there are 3 of them. So how to build this tree here? So you can consider H, okay, and then YH, and then Y square H. Okay, so these are the 3 concepts you have. Okay. So you can see that this concept not necessarily is a group, right? Because you see C2 and C3, there's no identity here. Okay, so that's why we won't call coset a group. Because coset in general is not a group. Okay, there's no identity, for example, in C2 and in C3. Okay, only this have the identity because this is the subgroup itself. Okay, so just now what did we discuss? So S3 will add on S3 mod H. Okay, I will add on this S3 mod H. And this action is actually transitive. Okay, it's transitive. Okay. Okay, it's transitive. Okay. So what's going on here? So we also can consider another case. S3 add on the set 1, 2, 3. Okay. S3 add on the set 1, 2, 3. So where how we correspond these two actions together? How we correspond these two actions together? So we can let S add by 2, 3, and then Y X Y 1, 2, 3. Okay. So these two are the same. Can you see why these two are the same? So let's think about it. So why is these two the same? So just now we model out by stabilizer, right? Stabilizer here. So this means what's the thing that's stabilized by H? What's the thing that's stabilized by H in 1, 2, 3? In 1, 2, 3 here, what's things stabilized by X? What is fixed? 1, 2, 3. What is fixed by 2, 3? 1. Okay. So we can see that B, C, and then 2, 3 fixes 1. Okay, we see that 2, 3 fixes 1. Okay. So meaning what? G of 1. Okay. The stabilizer. So let me put like this. The stabilizer G of 1 equal to what? Equals to 1 identity and 2, 3, which is equals to the H. Okay. Okay. Yeah. No. Okay. But just now it says what? Just now it says that there's a bijection. Again, there's a bijection between S3/H by theorem. Orbit stabilizer theorem. Orbit stabilizer. The theorem. What did the orbit stabilizer theorem tells you? There is a bijection. Okay, so there is a bijection between S3 mod H with OS or all of S, correct? So just put all of S. Okay. And there's a bijection between this. So what's this bijective map here? Okay, so here we consider what? Consider H equals to G1. And then here we consider O equals to O1. Okay, so there's a bijection between these two. Okay, there's a bijection between these two. Okay, but just now, when we quotient S3 by H, what do we get? How many things we get here? How many things we get? How many things we get here? 3 things, right? That means this orbit here also should have 3 things. Okay, so what are the 3 things here? Orbit of 1. What's the 3 things in this orbit here? What's the 3 things here? So here got what are the 3 things I have? So I have H. Okay, I have H, I have YH, I have Y square H. Okay, these are the 3 things I have. Okay. So under the orbit stabilizer theorem, right? So what's H should go? So I should take identity add on my 1. Okay, I should use identity add on my 1, which I just get 1. Okay. Okay, remember where this orbit stay in? It stay in my set, the set I add on. Okay, so 1 is inside my set, that's okay. How about Y? What is Y acting on 1? Okay. Y here correspond to 1, 2, 3. This is my correspondent here. So I need to take 1, 2, 3, add on 1. So which is 真诚, which is 1. If I take 1, 2, 3 acting on 1. No. So this is a thing in my group. Okay, so this is a thing in my group. This is a thing in the set. Okay, so we need to consider how S3 add on this set here. So how 1, 2, 3 add on this set? It sends 1 to 2. Okay, it sends 1 to 2. So 1, 2, 3 add on my set sends 1 to 2. Okay. Does it make sense? Okay. Sends to 2. Okay. And then how about y square acting on 1? Y square is what? Y square by my definition is 1, 2, 3 square acting on 1. Okay, 1, 2, 3 square is what? 1, 3, 2 on 1. So 1, 3, 2 on 1 is what? 3. Good. So you see, what's the thing in my orbit? There are also 3 things in my orbit. Okay, so these 3 things here correspond to the 3 cosets here. Okay, no, so this is the bijective, the epsilon. Okay, 3 things in my left coset correspond to 3 things in my orbit. Okay, so this is a very strong theorem because we can study groups element using actions. Okay, how I study rotation, I just see how my ball rotate. You know, how I study, for example, reflection of this whiteboard. I just see how this whiteboard changed. You know, you get what I mean? So this group action is very concrete. You can see it on the set. Okay, on the physical item. Can you get my message? Okay or not? Okay. Like how if I apply symmetry on this paper, okay, I can flip it, I can rotate it, I can translate it. Okay, how do I study this group element? I just see how my paper changed. If I reflect it, it become like this. If I translate it, go here. Okay, I just look at how my object here changed. Okay, don't just tell me I shift it, I shift here, I shift there, I shift there. Tell me, you can tell me where's the location, and I also can study the action. Does it make sense? Make sense or not? Okay. Okay. So actually this theorem kind of makes sense, you know. Why make sense? We are quotienting out what? Stabilizer. What does stabilizer do? Stabilizer fixes stuff. Stabilizer don't get your element to anywhere else. That's the thing inside the kernel of action. Right. That's why we kill all the kernel. We don't want to look at them. I just want to look at those group elements that can move my object non-trivially. Okay, no. If you just take things in the stabilizer and add on my x, then you are like doing nothing on my object. Okay. So after you modeling out by the stabilizer, these are the things that move my object non-trivially. Okay, no. Okay. Okay. I kill everything that fixes my object. Question. Yes, yes. So basically, you kill all the things that get sent to identity. Yes. Okay. You kill the thing that sends to identity. Why I also kill the concept? Why I also kill the concept? Because if you take a h on one, h is still acting like a identity. I don't care. I just care about the things that do non-trivial stuff to my object. Okay, now that's why this concept makes sense and very important. Okay, because you would have composition like y with some hash. But this hash here is a stabilizer. It fixes my stuff. I don't care. Okay, I don't care. I just care about the thing that do non-trivial action on my object. Move it from one, move to two. Okay, all the thing that get fixed is in the hash. You see, everything fixed here. No matter what hash here, e little h, one also one. Okay, no? Yeah. Okay. So it means what? All the little hash here is just acting like the identity. Real. Because all the little hash here fixes one. For example, in this case here, 2, 3. 2, 3 acting on one is just like identity acting on one. Okay, now this is the action of this map here. Sense? Okay. Okay. So this map is not some trivial map. It's telling you how this element here, set of element here, acting on one. Okay, how they act? They just act like they are representative. Okay, they just act like they are representative. Okay. Any question? Okay. If not, let's continue. Okay. So you can see that we have these group, right? Subgroup, right? So we can again count. Okay, we can again count our group. Okay? Count the cardinality of our group. So consider a group action X with our S is a finite set. Okay, then for all S in X, so we fix one of them. Okay, we fix one of them. We look at the stabilizer. We look at the orbit. Then G, okay, is partitioned by the orbit. Okay, it's partitioned by the orbit of X. And then what's the number left here? This is actually the cardinality of my stabilizer. Okay, so in other words, order of G is equal to order of stabilizer times order of orbit. Can you quickly see why we can do this? Just by the previous proposition. Okay, just by the previous stabilizer theorem. So let's prove this. So by counting formula before, okay, by the previous counting formula, we have that G is equals to Gx times the number of coset of Gx. Correct? Gs is the subgroup. Then we can consider the set of coset. Okay, but what is the set of coset here? This is exactly how many number in the quotient group, right? Okay, this is exactly how many elements inside my quotient group. Number of coset. Number of coset. Okay, set of coset. Number of coset meaning the cardinality of the set of cosets. Does it make sense? Okay, so this is a, by definition, set of coset. Number of coset. Okay, so cardinality of the set of coset. But this one, what we have done just now, we have built a bijective map between set of coset and orbit of S. Okay, so by the orbit stabilizer theorem just now, we have the cardinality of Gx times the cardinality of Ox by stabilizer orbit stabilizer theorem. Okay. Okay. Yeah. Yeah, S is in S because
The last example I see that
where? Which one? Huh? Differential orbit. Yeah, I think last time I changed it, right? Wait, let me see. You mean the new one here? Is it the one I posted? Huh? Okay, so where is it? 18, yeah. 18. Let's wait, let me see. Yeah, correct. Yeah, so I forget to fix this. I realized this when I do lecture yesterday, but I forgot to fix here. Okay, yeah. Thank you. Yeah. Okay. Yeah. So I mean, there's a reason why we put little s r small g, because we want to talk about something inside the set. Okay. So just be aware. Okay. 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 So this is the counting formula here. Okay. So let's keep going. So definition. Okay. So we're gonna define what is the permutation representation. Okay, so what's the permutation representation of a group? G is a homomorphism. Okay, is a map again, but this is a strong map, is a homomorphism. And then there's a permutation here, right? So you should think of how this permutation pop up in this homomorphism. Okay, and then you have a group G. So you have G, you have permutation. So how these two things relate together? Okay, so you have a group homomorphism from G to a symmetric group. So it's, in other words, a phi from G to Sn. Okay, so meaning what? I give you an element in group. Okay, you tell me how to permute n indexes. This is the definition of this map. Permutation representation. Okay, give me a group element. Tell me this group element how to add on n indexes. This one is very natural, right? Do you think this is natural? Do you think this is natural? Why is this natural? What's the natural n you can take here? You can take this n as the number of element in your group. And then the element of G will permute the group element. Remember the Kelly theorem? Remember the Kelly theorem? It's the same thing. Okay. Yeah. But this one is more general. Any Sn. Okay. So what's the proposition here? Let G. Okay, so I just give you an example here. Consider S of G. Okay, meaning G permutes elements in G, or I say all the element G in G permutes elements in G. In which case my Sn is S of the cardinality of my G. Okay, so I associate G1, G2, G3, G4, G5, Gx, G6, right, to 1, 2, 3, 4, 5. And then I see how this Gi get permute, and then I'll see how this number get permute. Does it make sense? I name my element in G by G1, G2, G3, and so on. Okay, and then I see how these Gi get permutes under a fraction of G, and then I'll see how the indexes get permute. So the indexes is the n indexes. And how many of them? They are cardinality of G of them. Okay, if you G sign. You can write it down. Okay, so what's the proposition here? So let G be a group. Let G be a group that exists again a bijective correspondent. So you in our class you see a lot of bijection, right, or isomorphism. Because really we want to make connection between different things. Okay, we want to make connection with a lot of things as possible, as many things as possible. Okay, this is the essence of abstract algebra. Okay, so we want to make connection as many as possible. Okay, so if you are alone, then it's very hard to study this course. You need to make a lot of connection so that you can open up, widen up your mind. Okay, otherwise, you're very hard to accept this concept. Okay, because your attitude is against with this course. This course is trying to make more connection, many connection, as many as possible. Okay, so let G be a group. There exists a bijective correspondent between group actions of G on the set 1 up to n and the permutation representation G to Sn. Okay, so if I collect all what I say here is, if you give me a group action, okay, of G on X, then I can give you a permutation representation. Maybe this is not clear enough. Okay, let's make it mathematically clear. Okay, so what is the group action does? So to talk about group action, you need to tell me, okay, how the group acting on S. To tell me how group acting on S, you need to tell me for every element in G, how does this G act on element in S? Okay, so meaning for every G in G, okay, I have a map. This is what we call the multiplication map or operation last time. Okay, so every G, Okay, every G is a map from S to S. Okay, this is what group action tells you. So if I tell you a group action, I need to tell you how the group elements add on my set S. Alright, this is group action. So given one group action, how do I produce a permutation representation? Meaning, how I produce a map from G to Sn. And how do I produce that? How do I produce that? Okay, what do I do? I just send it for a permutation that send G to MG. That's all. Because MG is a permutation. Because MG is a bijection. Why is it MG a bijection? Because this map is invertible. Why is it invertible? What is the inverse result? What is the invertible of this? What is the inverse of this map? What is the inverse of MG? If you send S to GS, how to send GS back to S? Huh? Venus, you want to say anything? What do you say? Sorry? Over G? Over G means what? You cannot always produce fraction, right? So meaning you need to take G inverse. Okay. So you multiply by G inverse. So meaning MG. So let me write here. So M of G inverse is the inverse of MG. Okay. So you need to check. S go to S using MG inverse is the same as identity map. Okay, it's the same as identity map. And also S go to S using MG inverse first, and then MG is also an identity map. Okay, you need to check this too. Okay, so you need to check. Okay or not? Okay. Does it make sense? Okay. Okay or not? Question? Jimbo got problem reading this? Huh? Oh, okay. Yeah. Okay. So what's the next thing to do? So we want to show that this blue map here is actually a homomorphism. Okay, you need to show that this is a homomorphism, and then what else? You need to show that this is a homomorphism, and then you need to show that this is a bijective. Do we want to show this is a homomorphism or not? No, we just show that this is a bijective map. That's all. Okay. Yeah. We just show that this is a bijective map. And then it defines the right map. So meaning if I send this element here, okay, to element here, okay, this P here have to be a homomorphism. So you need to check that G sends to MG define a homomorphism. Okay, so that this map is well defined. Once you have this homomorphism, right, you send this back to group action, this is automatically true. This is automatically true. Does it make sense? Yeah, no. So if you have right hand side permutation representation, if you send it back to group action, this MG automatically give you the group action because you just need some MG that permute the group. This is what the MG does for you in Sn. Okay. But if you want to go from the left to right, okay, you need to show that this phi is actually a permutation representation. Okay. Which means what? this permutation representation is a homomorphism from G to Sn. So you need to show that sending G to Mg is a homomorphism. Okay, maybe let's do this first. So I'll prove. Check that the left to right, the left to right map is a homomorphism. Okay, so that is phi of GH is equals to phi of G times phi of H. Okay, but what does this mean? So what does this phi do? Phi send G to Mg. Okay, phi send G to Mg. Okay, so it means that phi of GH is MGH is equals to Mg times MH. But how do we show this is true? How do we show this is true? This is an equality on function. So I need to check on element. Okay, so this is true if it is true on all the element S. For all S in S. Okay, so this part here is what? Equality of function. Okay, but what is MGHS and MGMHS? What is this? MGH on S is what? Right multiplication by, left multiplication by GH on S. But on the right hand side, what do you have? You multiply by H first and then multiply by G. And then what is this? This is a group action. Okay, so this is true, which is true by group action axiom. Okay, so one thing to not to get lost in pure maths class, right? You need to keep a list of definition beside you. If you don't keep it in your mind, you need to keep a list of definition beside you. Otherwise, you will get lost, because the reason you get lost is very easy. It's simply very easy. You don't know the definition. That's all. Okay, so you need to recall the definition always in pure maths class. Okay, please remember, the only reason you get lost in pure maths class is because you are not familiar with the definition. So make sure you keep a list of definition beside you. It's not in your mind. Okay, you should keep in your mind actually. Okay, this definition. Okay, no? Yeah. So every time you get lost, please go back to definition. Okay. Yeah. And then I think I'll left you to show it is bijective. Right. Show it is a bijection. Right, proof bijective. I will complete it in my notes. Okay, try and prove that it is bijective. So for example, what? So for example, you can consider a group, the dihedral group. Okay, so last time we already know that the dihedral group is the same as S3. Okay, so what's dihedral group? It's the symmetry of equilateral triangle. Okay, so you are permuting the vertexes V1, V2, V3, 1, 2, 3, the vertex of equilateral triangle. And then this is in bijection with the permutation matrix representation from D3 to S3. Okay, by this example here. So what does it mean? Here we are playing around with triangle, but here we are playing around with 1, 2, 3. Okay, no? So on the left hand side here, we are playing around with triangle, right? The V1, V2, and V3. But on the left hand side here, on the right hand side here, we are playing around just by 1, 2, 3. So we abstract again. Okay, somehow we don't care about the edges anymore. We just care about how the vertex move. Okay, no, abstract again. So we're abstracting ideas. Actually, we don't need to care about how they connect anymore. I just need to care about how the vertex move in the end. Does it make sense? Okay. 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 Yeah. So this is the idea of the theorem here. Okay, I don't need to care about the structure of my set. I just need to care about the point, for example. Okay, for this example here. Okay, so similarly, I don't want to copy anymore. So you can replace Sn, okay, by any S, literally by any S, not just 1, 2, 3 until N. You can replace with any S, and then you look at the homomorphism from G to permutation of X. So you permute the element next. Okay. And then the last important thing is the group action is faithful if the corresponding permutation representation is injective. Okay, if this homomorphism is injective, we will say faithful. What does it mean? What does it mean here? What does it mean here? Faithful is what? Lawyer. Why is it lawyer? Huh? Zhongchen, yes, Zhongchen. Why is it lawyer? Why is this group action lawyer? Because I can study the group just using the permutation. I can just see how the group acting on the object. I can study the group. Okay. So meaning what's in the kernel? The only thing in the kernel is identity. There's nothing else that can fix my object. There's only identity can fix my object. Then I can study this group just by seeing how my object gets changed. So I can see all my group elements using my object here. Rotation is just an idea, right? I just rotate. But when I rotate on this pen, you can see how this pen get rotated. So I can study the group elements using my object here when my group is faithful. My group action is faithful. Okay, so I give some example what kind of action is faithful. For example, I acting on the congruence triangle is faithful, and then GL2, Z2 acting on this tree set is also faithful. Okay. Yeah, once you read this, I think you can read my paper already. I will post my paper online for you to read. Good. What you get. Yeah. And one of them is almost on the stage of publishing because we already done all the typo fixing, and I think the next email we'll be getting is to publish. I think it's before Christmas. Hopefully before Christmas, I can share you. One of them is 81 page. One of them is 18 page.
So it's your book. Your book.
These are from my thesis. Yeah, a faithful group action. Yeah, faithful group action. Yeah, you can come. Yeah, faithful group action. Okay, so let's see. Okay, we'll see you next week. Ring. Hello. Next week we'll enter ring.